Okay, so here's just a walkthrough of the sound problems in case you need them. I'm going to use my very exciting rainbow pen for this. Let's make sure it's on the right sort of setting. Yes, okay, it's there now. So, question one, got a microphone connected to the oscilloscope, display a sound wave, shows this following trace. How many time periods are shown on the trace? Well, we've got 1, 2, 3. So we've got there 3. What is the frequency of the sound waves? Well, we need to know what in the x direction is represented. So 1 square is 0.001 seconds. So that means the one time period is equal to 0.002 seconds. So we'd say, so there'll be 1 mark for recognizing that. So t is equal to 0.002 seconds. So we have 1 over 0.002, which is 500. So, of course, 1t. I'm actually going to have to switch off that because that's going to annoy everyone. So we've got 500 hertz. On the grid below, sketch the trace of a sound wave with a smaller amplitude and a higher frequency than the wave shown by the dotted line. So smaller amplitude means it's not going to go so high. Higher frequency means I'm going to see more waves. Let's go with green. So as long as I'm kind of consistent and I've got lots of waves and a small amplitude, I'm just trying to be reasonably. There we go. That'll get you the mark. So because the height isn't so big and there are more waves. You know that's quite Question 2. What is the frequency range for human hearing? 20 to 20,000. So that would be A. Oh look, it's another oscilloscope trace, and oh look, it looks very similar. So we've got calculate the frequency of the sound wave. So we need to look again. We need to measure the time for the whole thing. So we're told that is 0.005. So we've got 2 of these. So that time is equal this time. So time is equal to 0.01 seconds. So we would get f is equal to 1 over t. Notice this time is going to equal 1000 hertz. The student empties some water in the bottle, blows over the top. The sound produces the same loudness but a lower pitch. On the diagram, draw a trace of this new sound. So this time, remember, okay, so same loudness. So that means we're going to have the same amplitude, lower pitch, see fewer waves. So same loudness. So I mean, even though that's so terrible there. And there we go. So, so there we go. 1 mark for making sure it's the same height, another mark for making sure that the frequency is the same. This question is about sound waves. Sound waves. Oh, sound waves are longitudinal waves. There we go. Describe an experiment to measure the speed of the sound in air. So, if we think about this, what am I going to put in? I'm going to say, I'm going to have a friend fire a smoke pistol from a distance of, let's say, 250 meters using a stopwatch. Okay. Oh, actually, I'm going to measure that distance as well. So measure with a trundle wheel. I don't know whether they're giving me email for measuring with that, but I'm going to check. Using a stopwatch, time, how long, using a stopwatch, actually, I've changed it slightly, so start timing when you see smoke, stop when you hear sound. Okay, so using a stopwatch, start time when you see smoke, stop when you hear sound. Calculate speed using distance over time, and I'm going to then repeat and average. Okay, so notice that what's quite clear here, what am I making sure that I'm doing in a describing experiment thing? Well, what am I ticking off? I'm ticking off some way, I've got some method that makes sure that there's something that I can both hear and see. I've selected a distance which is big. I've given a measuring device to measure that distance. I'm going to measure a time. I'm giving something to measure that time with. I'm describing that I start when I see the smoke, stop when I hear the sound. I'm saying the equation I'm going to use, I'm going to repeat, and I'm going to do an average. And I'm pretty sure that ticks off everything you need to do there. Look at the bullet points. Okay, so cross C, use the graph to estimate the speed of sound in air 6,000 meters above sea level. So essentially this is about reading off on the graph. It's quite hard to do because it's coming up on a screen. Yeah, that for me is around about 316 meters per second. Describe the pattern shown by the graph. Okay, so it is a linear relationship because it's a straight line. Okay, and I'd say as height increases, the speed of sound decreases. Okay, so that can also be said straight line. And then we've got this wonderful confused looking student. This person has appeared in so many, and she must be like in her late 20s by now. Some aeroplanes can travel faster than speed of sound. When an aeroplane travels faster than it was a shockwave, people on the ground hear this shockwave as a sonic boom. A student says it is easier for an aeroplane to make a sonic boom when it travels higher up. Do you agree? Explain why. Now, questions like this, there is never a mark for your yes or no. Okay, that actually doesn't get a mark. What you get the mark for is why you're saying that. Okay, so do I agree? Easier for an aeroplane to make a sonic boom when it travels higher up. I'm going to say that I agree. Why do I agree with that statement? Well, to make a sonic boom, you've got to go faster than the speed of sound. If you're higher up, the speed of sound is less. Okay, so it's easier. If you're at 10,000 meters above sea level, you've got to travel at over 300 meters per second. If you're 6,000, you've got to travel faster. You've got to travel 16 meters per second faster. So my statement for agreeing, so I'm going to say, do I agree? My answer is, in this case, I agree, yes, and then it's because. Speed of sound decreases with height. Okay, therefore it is to travel faster than sound at higher altitudes. And there we go. And that's my answer to that one. Okay.